Good morning. Today I'm going to explain why the gradient of a given function is the direction of steepest ascent through visual intuition. Before that, I need to give some introductory words which will help later on in the understanding. First, have you ever seen before that both functions, that is, the given function and its gradient, are settled in the same picture? I want to begin by explaining why the first function can take z values, which is the orange graph, while the gradient is trapped in the xy plane where z is equal to 0, as this is very important. For this purpose, we gotta realize an important difference between these two functions. The function we begin with, which we wanna take the gradient of, takes in two inputs and returns one unique output, which is the z value for every xy pair. This is why it ascends into the z plane, while the gradient, which is the collection of partial derivatives in vector form, takes in two inputs and returns two outputs. In other words, taking an xy pair and output a vector constituted by two components. Since we only have two independent variables, which we are taking the partial derivatives of, a vector of just two dimensions will be graphed, and this is represented on the bottom, where for every xy pair, a vector emerges whose components I hat and j hat are the partial derivatives. If we had a function of three variables, then these vectors would have raised and taken z values, because now they have a third component. This is the reason for which the graph of the gradient of a two-variable function is confined in the xy plane, where z is equal to 0. Now, we're going to deal with the fact of why do these vectors point in the direction of steepest ascent. For this purpose, let's begin with a simple function. Say f of x, y is equal to x. This is its graph. Right off the bat, you would say that the steepest ascent should be towards this direction, right? But why? Well, first, you should know that the scalar quantities of I hat and j hat are the partial derivatives. For I hat, in this particular example, its scalar is partial of x, while for j hat, it's partial of y. Notice that if I only care how does the function f changes as x moves forward, the rate of change will be 1. And this rate of change of partial of x will be the scalar quantity of the unit vector I hat. Therefore, a unit vector I hat will emerge on a plane scaled by a factor of +1. Which means drawing it towards the direction of positive values of x, because it takes the x-axis as a reference for being drawn, while on the other side, the function f does not change as y moves forward, therefore the partial of y is 0, so there will emerge a unit vector j hat scaled by 0, which virtually means no vector. Finally, we join both vectors, that is, partial of x I hat and partial of y j hat, tail to head to determine the direction of the gradient, which in other words is the sum of the mentioned vectors, partial of x I hat plus partial of y j hat. And notice, it points straight to the direction of steepest ascent. Now, suppose the function was f of x, y is equal to y. Then these vectors will now point towards y, stretched by a unit of 1. And this is because now the partial of y is different than 0, while the partial of x is 0. Okay, but what would happen in the case where we actually have partial derivatives greater than 0 for both directions, as in the function f of x, y is equal to x plus y? Well, vectors whose components are I hat and j hat, each having a scalar equal to the partial derivative they represent, that is, a value of 1, will emerge on the xy plane, neither all the preference to this side nor to this other side, but equally shared. And hey, that's just exactly the direction of steepest ascent of this function. If we made 3 times bigger one of the partial derivatives, then the components I hat and j hat will adjust themselves so that they always point towards the direction where the function increases the most at a specified point we're inquiring. As you can see graphically, the plane f is equal to x plus y has a smooth slant. The direction of steepest ascent should be towards there, but g is equal to 3x plus y has a sharper slant. There is no possibility that the direction of steepest ascent is the same. The vector, which represents the direction of steepest ascent should have a little more strength in the x direction to keep that title. You can compute the gradient of g is equal to 3x plus y to verify this statement. What if now we're dealing with negative slopes? Let's take for instance the function f of x comma y is equal to negative x. As we go on from left to right measuring the partial derivative of the function with respect to x, in this scenario it's going to have a negative value, which will be negative 1. In this case, a unit vector I hat will emerge having a scalar value equal to negative 1. Since the unit vector I hat takes the x-axis as a reference for being drawn as well, then its direction should be towards the opposite side, rendering it with a scalar value of negative 1. The same thing with f of x comma y is equal to negative y. The vectors will point in the opposite direction of the negative slope, because the j-hat unit vector takes the y-axis as a reference for determining its length and direction. The gradient is a function that draws a vector field. You can see that coincidentally, no matter what you do, taking the partial derivatives of a given function and setting them to be the scalars of the corresponding unit vectors, no matter if the slopes of the partial derivatives are negative or positive, it will always render a vector pointing in the direction of steepest ascent at a specified point. The examples we considered were of course simple, in that we had constant partial derivatives. Before wrapping up, I wanted to add something as a bonus to the pondering of this topic. The gradient and the fact that it points towards the steepest ascent is even simpler than what I just presented. Suppose I have the function f of x comma y is equal to 9x plus y. This is its graph. I don't want you to think about numbers for a moment, just focus on the graph. In this high slanted graph, we would be tempted to say, just by looking at it, that this should be the direction of steepest ascent. And that's a good supposition, but let me ask you, what does make the function f increase the most? By one step making it increase by 9 units, or the case where we also add up 1 unit when moving a step in the positive y direction? It's pretty obvious that f would increase the highest if we factor in both contributions. The gradient in itself indicates that we shouldn't be narrow-minded trying to increase the f function by only moving in a direction. Hey, here's an uphill in the y direction having a slope of 1, which will add up 1 to my increase in f for the same step length that I'm taking as I move in the x direction. We should also consider it then. The fact that the gradient points in the direction of steepest ascent is because one is being greedy enough to not only seize contributions of one direction for the increase of f, but also the other direction. The vector of the middle is the scenario where we take advantage of all the contributions, which is the direction of steepest ascent of f.